go have two sections, section A and section B. In section A, you've got 20 questions, of which 4 possible answers are provided in A, B, C, or D, and you have to choose the best possible answer. In section D, you've given questions, you have to answer all the questions in the spaces provided on the question paper. So let's go ahead and answer section A. We're going to start with the first question. Answer all questions on the answer grid provided. So A1 said, how many significant figures are in 2.0800? So how many significant figures do we have in this figure, or this number here? So when it comes to significant figures, you have to know that non-zero digits are significant. A zero between two non-zero digits are considered significant. So there are two things that you should look out for when we're talking about significant figures. The first thing, on number one first, you're talking about the non-zeros. So every non-zero is significant. Every non-zero is significant. And two, you should look at the zeros. So any zero between two non-zeros are considered as significant. So zeros between non-zeros are considered significant. And let me add a third one. The third one will be that zeros at the end of a decimal part are considered significant. They are significant. That is zeros. So if you have a decimal and then you have a zero at the end of a decimal part, so these zeros are considered to be significant. Okay, so let's use this to check how many significant figures here we have. So this is a significant figure. So this zero here, is it significant or not? So it is significant because it's between two non-zeros, which is one is between two non-zeros, two is after the decimal part, so 2.0. so after this part it is significant, and 8 here is also significant, and trailing zeros after the decimal point are also significant. So these two are also significant. So the zeros after the point, the decimal part, they are all significant. So 1, 2, 3, 4, and 5. So here we have 5 significant figures in this part. In other words, we can say zeros to the left of the first non-zero digit are not significant. Zeros to the first non-zero digit are not to the left of the first non-zero digit are not significant. So for example, I'm talking we have 0, if we have 0.001, then these zeros, they are to the left of the first non-zero digit, hence they are not significant. If they are to the right, then these will be significant. Alright, so that is the situation that we have here. Alright, so let's jump to question 2. Which of the following contains base physical quantities only? So we're talking about the quantities which can be measured, or in short with the SI units for quantities. And length, we know the measurable ones, kilometers, mass in tons. So these not like the SI unit for length. So again, here you see length in kilometers, so we can cancel out A and C. Doesn't do for us here. D, we can see let's talk about B, length in meters, mass in tons. Not really. So we're looking for SI units for base physical quantities, which are quantities which can be measured. D, length in meters and mass in kilograms. So this is what we are looking for. These are the base physical quantities. The following diagrams show steps that a learner carried out in order to determine the volume of a wooden cock. Okay, so which one is the volume of the wooden cock? Okay, So these are what this learner did to find the volume. So number one, they collected water. Step one, in a beaker. The beaker was 100 mils or centimeters cubed, and then they added the cork and then the identical glass bulbs. Okay, there was a glass bulb before the adding of the cork, and then okay, so I'll be analyzing every question with you from the start so that I don't get too much ahead of you. I'll be also looking at the question from like a new point of view so that we solve everything together. So we'll be analyzing everything step by step together, so I don't want to be ahead of you in research. And so I'm just looking at the question for the first time as well, if you are looking at them for the first time. So which one is the volume of the wooden cork? So step two, they added there's the glass bulbs here, identical, there's this and that, and then the wooden cork is somewhere there. All right, so which one is the volume of the wooden cork? All right, so here there's a glass bulb. So if this was the initial volume, this is 20, then this is like halfway between 40 and 20, so this should be 30, and this is 40, and this is halfway between 40 and 60, so this should be 50. Right, so this was 50 initially, then after you add the glass bulb it goes to 60, which was this one right here. So this was 60 mils or centimeters cubed. So okay, so we know that the volume of the glass bulb here, it is 60 minus this one right here, which was 50. So we'll have 60 minus 50, that will give us a 10 mils or 10 cubic centimeters. So this is the volume of the glass bulb. Now it's one glass bulb. Now here we have got two of them. So anyway, we'll come back to the glass bulbs later, and then let's just look at the entire volume now, after adding the two identical glass bulbs and the wooden cork. So from here we go all the way to 100 centimeters cubed, and then that means initially, if you know, there are a couple of ways in which we can look at this. Every person can look at it differently, so we're going to look at it from this way. If I add one glass bulb here, it goes to 60, and this from 50 to 60. So if I add another one, I expect it to go an identical one to go 10 centimeters further. So from 50 to 60, it was 50, goes to 60. From 60 again to go another 10, so it will come to 70. So initially, after adding the two glass bulbs, before adding the wooden cork, we expect the level of water in this beaker to start at 70. If we add the wooden cork, now we are starting from 70. So from 70 we go all the way to 100, as it is showing there, to 100. So which means the volume of the wooden cork only, removing the volumes of the identical glass bulb, should be 100 minus 70 centimeters cubed, and that will give us 30 centimeters cubed. And that is how we can look at this question. So which one is the volume of the wooden cork? So the answer will be, the best option for us here will be A, 30 centimeters cubed, because we started at 50 right here. You add one glass bulb, it goes to 60, so meaning each glass bulb will give you an increment of 10. So if I'm at 60 and then I add another identical glass bulb, I'm expected to start at 70 centimeters cubed. Now if I'm at 70 centimeters cubed and then I added the wooden cork, and then it goes all the way to 100, so it means I have to subtract my initial, which was my final, which is 100, minus the initial, which was 70, and then I'll get 30 centimeters cubed. So let's jump to the next question. So we'll be kind of rushing so that we cover as much questions as possible in the shortest period of time if we can. Which of the following diagrams show an accelerating car? Which of the following diagrams show an accelerating car? So we've got distance here, time, time, distance. So which one is accelerating here? Alright, so we're going to eliminate those which are definitely not accelerating, or those which are just stationary. First of all, let us talk about acceleration. What is acceleration? So acceleration is the rate of change of velocity, okay, or change of velocity with time. So that is the rate of change of velocity with time, how velocity is changing in a certain period of time. So that is acceleration. So here we have got the distance from here to there, that is a distance, and then we have got the time here. So whatever time you have, the distance remains the same. So it means there is no any change in velocity. This vehicle, or this body, this car, is stationary at D, so it doesn't qualify, because at this point it's not moving. Why? Because the distance is just the same, just a straight line here, so it's on the same distance, so it's not moving. So let's look at DC. So I've got a distance here and time here. So right here we have got a constant. If you see this line here, it means that's a constant speed that we have, for constant velocity. So what happens when the velocity is constant? Now remember, we are saying acceleration is the rate of change of velocity. Now if it is constant, do we have any change? So constant means there's no change. So there's no change here in velocity. That means this car is not really accelerating, it's just moving at a constant speed. So C does not qualify. So I'm going to look at B. Let's look at B. So from here we see this car is not really having a constant speed. It's covering more distance in a shorter period of time, and the higher the distance, the more distance it's covering, the less time here it is taking to cover that distance. Hence, typically we can see this is the point which this is the graph which shows the acceleration of the car. This car is accelerating right here. It's going like sharp like that. So this one is accelerating. So this one, you see, as it's covering the distance, it's actually taking more time. The amount of time is increasing here. So this one here is showing a decelerating shape. So this one here is reducing the speed. Okay, so B is actually what we are looking for. It shows an accelerating car. A5. The diagram below shows a light bar PR pivoted at P, balanced by a 4 Newton weight and force F. So what is the reading on the Newton balance? So here we have this light bar PR. So PR is our light bar. So this could be a little bit intimidating. Look at the figures, the shapes and the diagrams and everything, like this has to be complicated. Well, it does get complicated if you haven't been learning, so you have to take the time to study now. And if you're looking for someone who can help you in tuitions and science tuitions and lessons, well, you are at the right place. You can call us. I think there'll be a number on the screen there. You can WhatsApp that line to join our tuition classes or our online tuition classes, and we'll gladly help you, prepare you for these for the science paper. Alright, so what is reading on the Newton balance? Okay, so not only science, biology, maths, and other subjects as well. So let's get back to the questions. PR, and we have got PQ here. What is the reading on the Newton balance? So this is the Newton balance. Now I want to check the reading here. So this reading is it reads the weight, right? The Newton balance, it reads the weight. So in short, we just want to find out what is the weight that has to be here at point R, okay, for this bar to balance, okay, by a 4 Newton weight and the force F. This is the force F right there. So first of all, where is the pivot? So we say light bar pivoted at P, so this is where the pivot is. All right, that's where the pivot is. Pivot is here, balanced by a 4 Newton weight. So where is the weight? This is the weight right here. Okay, that is the weight. So the action of the weight, is it downwards or upwards, this weight? So we see this should be downwards, right? This is pushing this bar downwards, right, like this. And then we've got a force F. This is the force F. Now this one here, is it acting, this force should be going in the other direction right there. Okay, so what is the reading on the Newton balance? So for us to be able to solve this puzzle, we need to know what we call the law of moments. The law of moments. Now the law of moments say that this, for a body to balance, the sum of the clockwise moments should be equal to the anti-clockwise moments, anti-clockwise moment. So we've got the clockwise moments, they should be equal to the anti-clockwise moments. Okay, anti-clockwise moments. So I hope you're seeing the scribbling here. So what are the moments that we have here? Which ones are the clockwise and the anti-clockwise moments? So this one right here, this force. So what is moment, first of all? So moment is also known as a torque. It's a turning effect of force, and its moment is equals to force times the distance. So this force right here, this is the anti-clockwise, this is the clockwise force, the clockwise moment right here. So if you want an in-depth lesson I've mentioned about the classes, you can join for these lessons and we'll learn together. So the clockwise moment here is 4, the force, clockwise force is 4, then the moment will be 4 times the distance from the point of application, the vertical, the perpendicular distance from the point of application to the pivot, which is 30 centimeters. Now remember, we're talking about base quantities, so it will be 0.3 meters. So that should be equal to this moment right here, this force right here, which is the anti-clockwise force, which is, we'll just say F because we don't know, times the distance from this to the point of application, which is the perpendicular distance, that is 30 centimeters plus 20 centimeters, which is 50 centimeters, which is 0.5 meters. I'm converting the centimeters to meters, that is by just dividing by 100, and I get 0.5 meters. So we say, and then we just solve this. So F will be equal to, so let me do this. So we'll say F times 0.5 is equal to 4 times 0.3. So let's pull up our calculator. So you can say we have 4 when we multiply that with 0.3, and we have 1.2. So we have 1.2, that is 4 times 0.3, that gives us 1.4, and then we're going to divide this value by 0.5, that's 0.5, and then we get 2.4. So fx here, sorry, f times 0.5, which is just f is equals to 2.4. that is, we multiplied 4 times 0.3, that is 4 times 0.3, and then we divide everything by 0.5, which cancel this one right here, and then we had 2.4 as the force, and then this is force, which should be in newtons. So this is reading on the Newton balance, so that will be 2.4 newtons. So this will be our best option. Alright, so let's jump to the 6th question. A car is traveling on a level road. Suddenly, the driver of the car sees a car crossing the road and decides to apply brakes. What are the energy changes as the car slows down? Okay, so as the car is slowing down, what are the energy changes? So we all know that energy can neither be created nor destroyed. It's a change of energy. So what are the energy changes as the car slows down? So is it chemical to kinetic and sound? Okay, is it heat to kinetic and sound? So a car is traveling. So look at the keywords in this question. A car is traveling. So how do you travel? You travel by moving, right? Okay, so from a car, the energy changes so that there is some kinetic. What is moving energy is kinetic energy, right? So we have to start with kinetic energy as the car is moving on a level road and decides to apply the brakes. Okay, so we have to start with kinetic. So from this perspective of the car, so A and B, we can do away with that. Okay, so suddenly the driver of the car sees a car crossing the road and decides to apply brakes. Okay, so what happens here? Do we, from kinetic, do we go to chemical? Since we've already cancelled A and B, they don't qualify since the car was traveling. So we have to start with kinetic energy. So is it, so the C and D, so is it kinetic to chemical, then sound? So like the car, I'm sure you've seen a car braking. I don't have to make that sound, but it does like make that sound when it's braking, when like just emergency brakes have been applied, and then you hear that loud sound. So it's kinetic. So that is the final energy you get. You hear the sound at the end. So there's kinetic at first, then we have heat and sound. Okay, so if you go to the tires of the car and try to feel them after the braking, there'll be some heat there. So the best option is kinetic to heat and sound, or kinetic to chemical and sound. So this will be our best option. A7, the graph below shows a cooling curve of a gaseous substance. Okay, so this is a cooling curve, and this shows the energy levels and the time taken. So E to F, F to G, G to H, H to I. Okay, so that's a cooling curve. In which states of matter will the substance be between point F and G? Point F and G. So F and, so if this is a cooling curve, so what do these level or straight lines on the graph show? So this part right here, E to F, shows the state that the substance is in. So this is in gas state. Since it's cooling, this is gas, and then so it's starting, the state is starting as a gas, since this is a gaseous substance. So the state, initial state, E to F, is gas. Then in the state of transition or changing, G and H will be a liquid state. A liquid state. So in this state here, the changing state, there will be a combination of gas. So it will be gas and liquid here. So in which states of matter will the substance be between point F and G? So F and G, it will be gas and liquid. F and G to be gas and liquid, which is C. So that is also known as the condensation point. The condensation point, F and G. 8. The following diagram shows a water wave. Which row gives the correct values of the wave amplitude and wave length? So we look at this wave and we have to check what is the correct value of the wave amplitude and the wavelength. So the wavelength is the distance between two crests or two peak points. That is, from there, the distance between these two guys is the wavelength, and then the amplitude is the highest point of the crest from the point of undisturbance, or the depth of the trough. That is the amplitude. So which row gives the correct values of the wave amplitude and wavelength? So the amplitude here, so it's from here to there, we have 8.0 centimeters. So this is not the amplitude. The amplitude is from here to there, or from here to there. That is the amplitude. So the amplitude definitely should be for half of 8.0, sorry, which is 4, and then, so which means C and D are not what you're looking for. So which is the wavelength? So the wavelength, we've said, is the distance between two successive crests, this and that is the distance. So if you look at this distance from here to there, it's the distance from here to there. It's the same, there is the same, and here to right here. So it's like you have 5 plus 5, okay, to make the crest, and that will be to make the wavelength, sorry, so that will be 10. So it will be 4, 10. The wavelength is 10 and the amplitude is 4. So A will be your correct option here. A9, the diagram below shows a learner in front of a loudspeaker that produces sound. So this is a loudspeaker area. The learner is here in the classroom wall. Which of the following diagrams best shows how the gaseous air molecules between the learner and the loudspeaker will move? So we have got the air molecules. How are they going to move? So sound waves are longitudinal waves, and the direction of the particles is in the direction of the movement of the wave. So, and the particles move, so the waves are not going to move perpendicular to the direction of the wave. They're going to move parallel to the direction of the wave, because this is a longitudinal wave, and so then they won't just move in one direction, because there'll be rarefactions and compressions. So our best option here will be A, will be the correct one, and it's what we are going to go for. So particle vibration will be back and forth. That is A. That will be the correct option. So let's jump to question 10. A girl of height 1.2 meters stands 4.0 meters in front of the plane mirror as shown in the diagram, in the following diagram. So I've got the girl of 1.2 meters and the distance from here is 4 meters. That is the mirror and the ground. How far is the girl away from her image? So with this question here, when you look into a plane mirror, a person's distance, the distance of the image for a person is as far behind or into the mirror as the person. So if you stand 4 meters away from the mirror, then your image is 4 meters, appears to be 4 meters into or behind the mirror. Okay, so that is 4 meters as well. So which means how far is the girl away from her image? So that will be 4 plus 4, which is 8. 11. A line JK drawn on a piece of plain paper on which a glass block is placed was viewed through the top, and its image was located using a pin as shown in the following diagram. if KL is equal to 1.8 centimeters and KM is equals to 4.8 centimeters, what is the refractive index of the glass? Okay, so we have this experiment used to view the line JK, and this is the line JK, and then they're telling us that wow, this is like a glass block. It's KM, and it looks too thick. Okay, but this is the eye. This is where we are looking at, we are viewing the line from, and then this right here is the locating pin. So now it's saying the image of this line was located using a pin. So this is where the image was located, and then we want to find the refractive index of the glass. So we're going to use the distance KL and the distance KM, that is the distance of the image, the distance of the object, to find the refractive index.